I want you to close your eyes for just a second and imagine the future.
Okay.
Not, the distant sci-fi future, but the one we are actively building right now. Picture it. You've got these rolling green hills covered in sleek, silent solar panels.
Right, the classic utopian vision.
Exactly. Offshore wind farms churning steadily in the ocean breeze, massive state-of-the-art artificial intelligence data centers just humming quietly, processing billions of calculations a second.
Yeah.
And it's all powered entirely by clean, renewable energy.
Yeah.
It is a beautiful, sustainable vision.
It is. And honestly, it's the consensus endpoint for global infrastructure. Like every major economy is funneling massive capital toward that exact horizon.
But, and this is a massive but, there is a completely invisible flaw in that vision.
Oh, a huge one.
Right. If we just snap our fingers and make that utopia reality today, like if we just plug all those gigawatt-scale solar arrays and wind turbines and hyperscale data centers into our current electrical grid,
It fails.
instantly, that beautiful green future instantly causes the entire electrical grid to violently collapse.
Yeah, we are talking about total catastrophic system failure here. I mean, protective relays trip, substations literally arc and meltdown.
Wow.
The lights go out, data centers crash, and the whole industrial base just grinds to an absolute halt. The sheer physics of the current grid, it simply cannot handle the volatility.
And the craziest part is the reason it fails isn't a lack of generation. Like we have enough wind and solar potential.
Right.
The grid collapses because we are missing a highly specific, totally unsexy layer of heavy hardware. We're talking about giant steel and copper coils, massive voltage regulators, industrial scale signal traps.
Yeah, metal.
Exactly. Without this heavy physical machinery acting as the intermediary, the green energy transition is physically impossible.
It is the great paradox of the energy transition, honestly. Capital markets talk endlessly about, the software of the future.
Constant.
Right, like AI load balancing algorithms, smart grids, clean energy credit trading. But the ultimate bottleneck isn't software.
It's metal.
It is raw, heavy, highly engineered physical equipment. Stuff that has to be manufactured, rigorously tested, and physically installed just to keep the alternating current of our electricity from tearing the infrastructure apart.
Okay, let's unpack this. Our mission for this deep dive is to isolate and examine the exact machinery powering this global energy transition.
I love it.
And to do that, we are zeroing in on a highly specialized, rapidly scaling manufacturer based in Sangli, India. They're called Quality Power Electrical Equipments Limited.
But we'll just call them Q-Power for short.
Right, Q-Power. We've pulled together a massive stack of market analysis, financial breakdowns, industry projections, all to understand how this specific mid-cap company is quietly riding a multi-decade global megatrend.
It is such a phenomenal case study in physical infrastructure. Like when you dig into their operational footprint, what becomes immediately apparent is that Q-Power is they're as far from a trendy tech startup as you can get.
Oh, entirely.
They don't have a SaaS multiple, they aren't selling software subscriptions, and they definitely aren't reliant on network effects. They deal in physical, heavy reality.
Yeah.
They operate at the very nexus of heavy industrial manufacturing and high-tech grid stability.
I really want to get tactile here and visualize what Q-Power actually builds. Because reviewing their product lines and the source materials, the terminology sounds incredibly dense.
It is very dense.
They operate in two main segments, right? First, you have power products, which includes things like reactors, transformers, and line traps.
Yeah.
And then you have their power quality systems segment, and that covers static VR compensators or SVCs, StatComs, and harmonic filters.
Exactly.
I know we throw these acronyms around, but let's ground this for the listener. What are these machines physically like? Like if I'm standing next to one?
Well, you have to start with the sheer scale. We are looking at extra high voltage equipment. Take a 765 kV transformer or a massive shunt reactor. You don't just load this onto a standard flatbed and drive it down the highway.
Right.
These are colossal multi-story structures. They are built from hundreds of tons of highly specialized, cold-rolled, grain-oriented steel.
Grain-oriented steel.
Yes, CRGO steel. It's surrounded by these complex copper winding matrices, all submerged in literally thousands of gallons of specialized insulating oil.
So just procuring the raw materials for a single unit requires a massive logistical operation.
Oh, massive. And that's before the engineering even begins. I mean, they take months to construct. They require immense capital investment just to set up the clean rooms for the insulation wrapping, not to mention the heavy-duty cranes for assembly.
Yeah, you mentioned 100-ton cranes in the notes.
Exactly. Exactly. And Q-Power makes its revenue purely by building this heavy hardware and selling it directly to global electrical grid operators, utilities, and large APC contractors.
EPC being engineering, procurement, and construction.
Right.
Okay, I understand the physical scale, but I want to push on the why.
Yeah.
Why are these specific colossal pieces of metal so absolutely critical to renewables?
Okay, good question.
Like, if I build a utility-scale solar farm, the photovoltaic cells generate the electricity, right? Why do I need a 100-ton reactor or a STATCOM sitting between my solar farm and the local city grid?
It comes down to the fundamental design of the electrical grid itself. For the last century, grids were built around the concept of baseload power.
Okay.
You had a massive coal, gas, or nuclear plant. And inside that plant, a heavy physical turbine spun at a perfectly constant speed, generating a steady, predictable, highly stable waveform of electricity.
Right, the grid was basically a one-way street engineered to take that stable baseload and push it outward to consumers.
Exactly. Supply matched demand, and the generation source was entirely within our control. You need more power, you just burn more coal.
Simple enough.
But renewables break that paradigm completely. Let's look at your utility-scale solar farm. It's noon, the sky is perfectly clear, and it is dumping hundreds of megawatts onto the grid.
Doing great.
But suddenly, a dense weather front rolls in. Cloud cover drops the solar output by, say, 70% in a matter of seconds. Or consider a massive offshore wind farm. The wind is howling, the turbines are maxed out, and then the wind speed drops abruptly.
The power output plummets instantaneously.
And in an alternating current grid, supply and demand must remain perfectly balanced on a second-by-second basis to maintain the grid's frequency, which is usually 50 or 60 hertz, depending on the country.
Why, I've seen those numbers.
When that solar output suddenly drops, the voltage across the grid sags. If the wind surges, the voltage spikes.
Okay.
If these fluctuations push the frequency even a fraction of a hertz out of bounds, the automated protective relays on the grid perceive a catastrophic fault. They literally trip the breakers to isolate the anomaly and save the physical wires from melting.
Which means a localized fluctuation instantly cascades into a rolling blackout.
Precisely. And this is where Q-Power comes in. Their products are the heavy-duty shock absorbers for that volatility.
Ah, shock absorbers.
Yeah, they sit at the substations and actively stabilize the erratic nature of renewable generation. They ensure that the waveform remains pristine, so the delicate electronics downstream, like, say, the servers in an AI data center, don't fry.
Okay, wait, let me test an analogy here to see if I'm fully grasping the mechanics, specifically regarding their high-end power quality systems like the STATCOM.
Go for it.
Is a STATCOM essentially acting as a giant industrial-sized surge protector combined with a battery pack for an entire metropolitan grid?
Well, it's a compelling way to visualize the outcome, but the internal physics operate a bit differently.
Okay, correct me.
A STATCOM, which stands for Static Synchronous Compensator, by the way, doesn't really function like a battery pack storing raw energy to keep a city running for hours.
Oh, it doesn't.
No. It's better to think of it as a dynamic, active suspension system for a high-speed train. A STATCOM manages what electrical engineers call reactive power.
Ah, reactive power. I've seen that term constantly in their technical specs. Break down reactive power for me. What is that?
Imagine you are pushing a heavy cart down a straight set of tracks.
Okay, I'm pushing a car.
The direct forward energy you apply to move the cart is the real power. That's the electricity doing actual work, like lighting up a bulb or spinning a motor.
Makes sense.
But imagine the track is warped, and the cart keeps violently drifting left and right, threatening to derail. You have to expend a significant amount of your own energy just pushing laterally, fighting the drift to keep the cart centered so your forward push actually works.
Wow, okay. So you were burning energy just to stabilize the system, not to move it forward.
Exactly. That stabilizing effort is reactive power. On a massive electrical grid, reactive power is constantly sloshing back and forth, degrading the efficiency of the lines and causing voltage instability.
It's like wasted effort.
Right. So a STATCOM utilizes advanced power electronics to monitor the grid's waveform thousands of times per second. Thousands. If it senses the voltage starting to sag because that cloud covered your solar farm, it instantly injects reactive power to prop the voltage back up. If there's a surge, it absorbs the excess reactive power.
That's incredible.
It continuously, instantly corrects the electrical waveform, it improves the power factor, and prevents the grid from basically tearing itself apart.
That dramatically shifts how I view these components. They aren't just, dumb, passive blocks of steel sitting in a field.
No, not at all.
They are incredibly reactive, high-speed architectural elements of the grid. And looking at their product specs, they are building this equipment for 765 kilovolt lines.
Right.
To put that in perspective for you listening, the power coming out of a standard residential wall socket is 120 or 240 volts. We're talking about 765,000 volts.
It's massive.
The sheer electromagnetic force pulsing through a 765 kilovolt lane rating wants to jump, arc, and ground itself through anything nearby.
Oh, absolutely. Designing a STATCOM or a reactor to handle 765 kV without melting into slag or shooting literal lightning bolts across the substage.
Literally lightning bolt.
Yeah. It requires materials, science, and electromagnetic engineering that very, very few companies on Earth possess.
Which naturally acts as an immense barrier to entry. I mean, you can't just raise some venture capital, lease a warehouse, and start shipping 765 kV transformers. The regulatory friction alone must be staggering.
The certification process is grueling. It requires extensive short-circuit withstand testing, impulse voltage testing, and years of proving historical reliability before a national utility will even allow you on their approved vendor list.
It demands a deep, geographically concentrated pool of specialized talent that you just can't spin up overnight.
Exactly.
That engineering mode is fascinating, but it forces a broader question. Building incredible, highly engineered hardware is impressive, sure. But to justify the aggressive capacity expansion Q-Power is undergoing, there has to be a commensurate, massive global demand.
Oh, there is.
Who is actually buying all of this stuff?
The addressable market is staggering, and the market analysis we have breaks the total addressable market, or TAM, down into highly specific tranches.
Let's hear the numbers.
So if we isolate the combined market for HVDC, which is high voltage direct current systems,
Right.
and
Yep.
FCTS, or flexible AC transmission systems, which is the specific category where STATCOMs and SVCs live, we are looking at a TAM of $15 to $23 billion annually right now in 2025.
Wait, $15 to $23 billion being spent every single year just on this highly specific stabilization and transmission technology.
Every single year. And the forward projections show that by 2035, that specific annual market will more than double, reaching $33 to $56 billion annually.
That is astronomical. Let's dissect where that capital deployment is originating, because the projections slice this market into three distinct layers of structural demand, right?
Yes.
The first layer is the global power transmission and distribution base market. We have roughly 8 billion people on the planet, and modern society requires electricity. Emerging markets are rapidly expanding their grid access, while developed markets are running on legacy infrastructure that is fundamentally breaking down. This baseline T&D market is estimated at $150 to $180 billion annually, but a massive portion of that is low-margin commodity infrastructure, basic distribution cables, wooden poles, standard residential transformers. Q-Power operates above that fray in a much higher value niche.
Which brings us to the second layer, grid modernization. This is the capital allocated specifically to HVDC and FACS systems. This layer is expanding incredibly fast because we aren't just building more grid, we are fundamentally altering how power moves. The HVDC segment alone is projecting an 8 to 12% compound annual growth rate.
Let's pause on HVDC because the physics of it perfectly illustrate why this modernization is mandatory.
Okay.
If you are building a massive offshore wind farm, you might be placing turbines 100 miles out in the ocean where the wind yields are highest.
Yeah, that's standard.
But then you have to transport that power back to a landlocked population center.
Right, and if you try to push that power through a traditional alternating current or AC submarine cable over that distance, you encounter a massive physical limitation. Well, AC cables essentially act like giant capacitors when run underwater or underground over long distances. They generate so much reactive power along the line that eventually the cable is entirely consumed just transmitting its own reactive current.
Wait, really?
Yeah, no real power reaches the destination.
So the traditional AC grid architecture literally defeats itself over long offshore distances.
Exactly. It defeats itself. The solution is high voltage direct current. You build a massive converter station at the wind farm, convert the erratic AC power into a highly stable flow of direct current, and push it hundreds of miles through an HVDC line with almost zero capacitive losses.
Ah, I see.
And then you use another massive converter station onshore to invert it back to AC for the local grid. HVDC acts as a lossless electrical superhighway.
That's brilliant. And then the third layer of demand is the direct renewable energy integration equipment. The global targets dictate that renewable capacity must scale from around 3,500 gigawatts today to somewhere between 6,500 and 7,500 gigawatts by 2035, just to meet net zero commitments.
It's a huge leap.
And the data shows that integrating every single new gigawatt of renewable energy requires between $2 to $5 million purely in grid integration equipment.
Yeah, the reactors, the harmonic filters, the StatComs.
So that direct integration requirement alone generates an implied market of $400 to $1,500 million annually, completely independent of baseline grid upgrades or offshore HVDC lines.
Exactly. But the most crucial distinction in the analysis here is the nature of this demand. The market isn't modeling this as a cyclical infrastructure boom.
Right, this isn't a temporary cycle.
No, the thesis relies entirely on this being a structural megatrend. This isn't tied to consumer discretionary spending or like a temporary economic stimulus. It is an irreversible, multi-decade shift forced by a combination of physical decay and regulatory mandates.
Now think about the physical decay.
Consider this. The average age of the U.S. electrical grid is currently 42 years old.
42 years old.
Yeah. A massive percentage of the high-voltage transformers and heavy grid components currently in operation were engineered with an intended 15 to 30-year lifespan.
So they are physically exhausted. The insulation paper inside the transformers is degrading. The copper is stressed.
They're ticking time bombs.
They have to be replaced, regardless of whether GDP is growing at 3% or contracting.
It is entirely non-discretionary capital expenditure. You just have to spend it. Now, layer the regulatory and consumption shifts on top of that decaying baseline. You have the European Union's sweeping Green Deal mandates. You have India aggressively pushing to reach 500 gigawatts of non-fossil fuel generation capacity by 2030.
Which is coming up fast.
Very fast. And perhaps the most violently disruptive factor, the electrification of transport.
The EV transition.
Right. The projections model global electric vehicle sales hitting 40 to 50 million units annually by 2035.
Think about the localized grid strain that causes. A standard residential neighborhood transformer was sized to handle a dozen homes running refrigerators, televisions, maybe an air conditioner.
Yeah, standard loads.
Suddenly, 4 of those homes install level 2 EV chargers and plug-in vehicles with 80 kilowatt-hour batteries at the exact same time every single evening.
It's chaos for the grid.
That localized transformer wasn't just under-designed for that massive simultaneous amperage draw. It was completely oblivious to it during the engineering phase 30 years ago.
EVs weren't even a concept for those engineers, so the local transformers physically overheat and blow out. Utilities are forced into a massive decentralized upgrade cycle just to handle the EV adoption curve.
And you combine that with the electrification of industrial heating, like commercial heat pumps replacing natural gas boilers.
Yep.
We are asking a 40-year-old grid to simultaneously manage wild, erratic inputs from utility-scale renewables on one end and massive, unprecedented localized demand spikes from EVs on the other.
The infrastructure is failing in real time.
Okay, I have to play devil's advocate here.
Sure.
If we are looking at a structural transition that spans the next 25 to 50 years, there's a massive risk of technological disruption.
Right.
Always a risk, yeah.
Yeah.
So what happens if a breakthrough in room temperature superconducting cables completely eliminates the need for reactive power compensation? Or what if solid-state microgrids become so efficient that we stop moving power over long distances entirely? Doesn't the rapid pace of tech innovation threaten to make all these giant steel coils obsolete?
It's a critical risk vector, definitely. But you have to separate theoretical physics from commercial grid deployment.
Okay, how so?
Breakthroughs in superconductors or decentralized microgeneration are absolutely happening in labs. But the horizon to scale those technologies, prove their 30-year reliability, achieve global anti-BEL accreditation, and physically manufacture them at a scale that can actually run a metropolitan area that is easily 15 to 25 years away.
And the grid operators don't have 15 years.
They don't have 15 months. The grid is buckling right now. You cannot power a massive AI data center coming online in 2026 or a North Sea offshore wind farm going live in 2028 with a theoretical superconducting material that won't be commercially viable until 2045.
Right.
The immediate non-discretionary need is for traditional, highly engineered, heavy hardware.
That physical reality provides a massive runway. But that runway leads me to a glaring contradiction in Q-Power's narrative.
Oh.
If this TAM is truly $15 to $23 billion, and it is a structural, non-discretionary necessity, then the giant legacy incumbents must be completely dominating the space. We are talking about global titans, Siemens Energy, ABB, GE Vernova, Hitachi Energy.
The big guys.
These companies have century-old relationships with utilities and R&D budgets that dwarf Q-Power's entire market cap.
And the data absolutely confirms that dominance. Over 80% of the high-voltage market share is concentrated within those legacy giants.
Meanwhile, Q-Power's current market share is estimated to be less than 0.2% of that TAM. It is a rounding error for Siemens.
Yeah.
So how does a mid-cap manufacturer out of St. Louis not just survive, but actively win lucrative contracts against multi-billion-dollar conglomerates?
By entirely avoiding a direct head-to-head confrontation. Q-Power has engineered a very specific, multi-layered moat designed to exploit the blind spots of the giants. It basically rests on 4 distinct strategic pillars.
Let's go through.
The first is pure technology specialization in extra-high voltage EHV.
Right, while Siemens or GE have to allocate resources across their entire portfolio, building everything from residential circuit breakers and gas turbines to nuclear plant control software.
Q-Power is hyper-focused.
They dedicate their entire engineering bandwidth to the hardest-to-build, highest-specification reactive power equipment. Because so few players can successfully engineer and certify 765 kV equipment, Q-Power avoids the brutal margin-crushing pricing wars that define the lower-voltage commodity transformer market.
Exactly. The second pillar is their international footprint, which is actually highly anomalous for an Indian mid-cap industrial company.
How anomalous.
Well, Q-Power actively exports to over 100 countries and serves more than 200 distinct global customers. A staggering 75.77% of their total revenue is generated from international exports.
Which completely inverts the standard model. Most domestic heavy manufacturers of their size might export 10, maybe 15% of their volume, relying almost entirely on domestic government tenders.
Exactly. And building that export network is an incredibly grueling process. Every single country, and often every regional utility within that country, has its own unique grid codes, harmonic limits, and vendor approval processes.
A regulatory nightmare.
Q-Power has spent the last 2 decades painstakingly navigating these regulatory labyrinths, securing utility approvals, and proving the reliability of their hardware in varied climates from the Middle East to North America. That accumulated regulatory capital and trust is a massive moat. A domestic competitor can't just wake up and decide to replicate 100 different international utility approvals.
The third pillar is their transition from a pure-play component manufacturer to an integrated ecosystem. They're utilizing strategic acquisitions to build a diversified power electronics platform. The recent moves really highlight this shift. They acquired a 50% stake in Sucrude Electric, and more notably, a 51% stake in Meru Electrical.
And those acquisitions are highly synergistic. By bringing companies like Meru into the fold, Q-Power internalizes the production of critical subcomponents, like specialized instrument transformers and high-voltage bushings.
So they aren't just bolting on revenue. They are securing their own supply chain for the most highly engineered parts of their STATCOMs and SVCs.
Right. They can offer a utility a fully integrated, bespoke, power quality solution rather than just selling them an isolated reactor.
But it's the fourth pillar of their moat that I think is driving their current valuation multiple. It's entirely rooted in macroeconomic timing. We're looking at a massive cost and timing advantage driven by an industry-wide capacity supercycle.
This is the crux of their immediate growth thesis. Because of the colliding megatrends, the aging grids, EV rollouts, renewables, the global demand for high-voltage equipment has violently outstripped global manufacturing capacity. We are in a chronic structural supply shortage.
Shortage of factories to build the things.
Yes. The lead times for EHV equipment have stretched to multi-year horizons.
So if a utility operator in Europe realizes they need a massive STATCOM installation to stabilize a new wind project, and they call one of the legacy giants today, the giant might quote them a delivery date in 2029 because their assembly lines are booked solid for the next 4 years.
The incumbents are completely capacity constrained, but Q-Power anticipated this bottleneck and proactively initiated massive capital expenditure programs to expand their footprint.
What does that look like?
They're currently doubling the manufacturing capacity of their Cochin facility. They are expanding the newly acquired Meru facility by 45%. They're bringing entirely new production lines online in Sangli.
It sounds like they are playing a brilliant game of musical chairs.
How so?
By expanding capacity right now during an industry-wide shortage, they are guaranteeing themselves a seat when the music stops, securing long-term contracts simply because they're the only ones who can actually deliver the goods.
That's a great way to put it. They aren't just competing on the technical specs of their reactors, they are winning contracts simply because they are one of the only certified manufacturers globally who can actually deliver the hardware within a 12 to 18-month window.
And that timing advantage creates a flywheel effect. Because they have available capacity, they secure lucrative, high-margin, long-term contracts. Those contracts provide the capital to secure raw material allocations from steel and copper suppliers ahead of competitors who are still trying to figure out how to expand their own factories.
Exactly.
Strategy is a great narrative, but it only matters if it translates into hard cash. Let's look at the financial engine driving Q-Power. We need to dissect their unit economics.
Okay, you can deconstruct their financial engine through a simple formula. Volume multiplied by pricing multiplied by mix. And currently, all three levers are compounding simultaneously, resulting in sheer hypergrowth.
Give me the numbers.
If you look at their trailing 12 months, their TTM revenue, it has exploded to 600 and 854 crores.
Wait, let's contextualize that velocity. 634 crores. We're looking at a company that previously operated with standalone fiscal year revenues hovering around 338 crores.
Yeah, it's wild.
Scaling to a TTM revenue of 854 crores represents an operational transformation that is almost hard to comprehend in heavy manufacturing. And the profitability is scaling even faster. Their net profit leaped from 100 crores in the fiscal year 2025 to a massive TTM of 301 crores.
The earnings expansion is aggressively outpacing top-line growth. And the core driver of that margin expansion isn't just that they're pushing more volume through the factories. It is fundamentally about what they're building. This is the mix shift.
Right, the mix shift. This is where the strategy materially impacts the income statement. Historically, a massive chunk of their revenue, around 50 to 60%, was derived from standard distribution and power transformers.
And standard transformers are vital to the grid, but from a manufacturing standpoint, they are highly commoditized.
Anyone can build them.
Well, there are dozens of regional players who can build a standard substation transformer. The bidding is intensely competitive, which suppresses pricing power and crushes margins. It is a high-volume, low-margin treadmill.
But Q-Power is deliberately evolving their revenue mix away from that commoditized baseline. They are aggressively prioritizing their power quality systems, the custom-engineered STATCOMs, SVCs, and extra high-voltage reactors.
Exactly. Because the engineering moat on a 765 kV STATCOM is so high, the competitive landscape shrinks to just a handful of global players. That scarcity provides massive pricing power.
What kind of margins are we talking about?
These advanced power quality products command EBITDA margins significantly above 20%. As these high-margin systems scale to constitute a much larger percentage of Q-Power's overall revenue, the company's blended margin profile structurally elevates.
And when you pair that margin-accretive mix shift with their capacity expansion, you trigger massive operating leverage. Heavy industrial manufacturing requires immense fixed costs. The capital expenditure for the testing labs in Sangli, the specialized 100-ton cranes, the massive clean rooms, the R&D overhead, those costs are sunk, regardless of whether the factory outputs 10 units or 100 units a month.
But the variable costs per unit, the direct labor, the specific copper windings, the CRGO steel core, are highly predictable and contained.
So as the new volume from their expanded Cochin and Meru facilities flows through the system, those massive fixed costs get broadly distributed across a much larger denominator of produced units.
Which means the incremental profit generated on every additional reactor sold is dramatically higher than the last. The financial model suggests that due to this operating leverage, a 10% increase in top-line revenue can drop down to a 20 to 30% expansion in EBITDA.
That's huge.
You see the sheer efficiency of this engine reflected in their return on equity, which sits at a highly robust 23.6%.
Okay, the income statement looks flawless. Hypergrowth, expanding margins, massive ROE. But looking at the cash flow statement from our sources reveals a massive point of friction. Year free cash flow conversion is sitting at a mere 13% of EBIT. If the operating leverage is so powerful and they're generating 301 crores in net profit, where is the actual cash? Why is so much cash tied up instead of flowing to the balance sheet?
It's a brilliant catch, and it exposes the grueling reality of operating a heavy B2B project business. The low free cash flow conversion is entirely a function of working capital constraints and an incredibly elongated cash conversion cycle.
Tell me about the cycle.
Q-Power isn't selling a consumer product where the transaction clears instantly. They are engaged in massive, highly complex, custom-engineered infrastructure projects for sovereign utilities and global EPCs.
The payment terms must be draconian.
They face very high debtor days. Consider the life cycle of a STATCOM order. A national utility places a 50 crore order. Q-Power immediately has to deploy massive amounts of cash to procure the raw copper, the specialized steel, and the microprocessors.
So the cash goes out the door on day one.
Exactly. But the utility doesn't pay the bulk of that contract until the unit is fully engineered, physically manufactured, shipped across the ocean, craned into a substation, electrically integrated into the grid, and finally certified to be performing perfectly under load.
And utilities often hold back a percentage of the contract as retention money for months after commissioning just to ensure reliability, right?
Exactly. That entire cycle can take anywhere from 9 to 18 months. And to complicate matters, Q-Power employs a just-in-time custom inventory model.
Just in time for massive steel coils.
Yeah. Because every single grid has unique harmonic profiles and voltage requirements, you cannot mass-produce STATCOMs and leave them in a warehouse. Every unit is a bespoke engineering project requiring specialized raw material procurement.
So as the company experiences this phenomenal hypergrowth, taking on more and larger international orders, progressively more of their cash gets temporarily swallowed by this working capital vortex.
Yes.
The profit on the income statement is real, but the physical cash is locked up in steel coils, sitting on cargo ships and retention contracts, waiting for utility sign-off.
It is the classic hypergrowth cash trap. The business is fundamentally healthy, but managing the liquidity through that elongated conversion cycle requires pristine treasury management.
Which means they need continuous, accelerating future demand to fund the massive working capital requirements of their current growth. Where are they finding that future runway? This leads directly into their strategic growth vectors for the next decade.
The strategic roadmap for 2026 to 2036 relies on 5 overlapping vectors.
Walk me through them.
First, operationalizing the massive capacity expansion we discussed to actually fulfill the demand supercycle. Second, deeper penetration of existing categories, aggressively bidding for larger HVDC and FACTS installations. Third, geographic expansion, leveraging their existing certifications to push deeper into emerging African and South American grids.
Okay.
Fourth, ecosystem expansion, utilizing acquisitions to internalize more of the high-value supply chain. And fifth, relentless premiumization, shifting the mix ever further toward bespoke power quality systems.
And the immediate catalyst giving these vectors immense credibility is their current order book. The filings reveal a massive 1,400 crore order book.
That is massive.
That is not a TAM projection or theoretical demand. Those are legally binding contracts waiting to be engineered and built. A massive domestic driver underpinning that backlog is India's non-discretionary target to reach 500 gigawatts of non-fossil fuel capacity by 2030. Integrating that staggering amount of solar and wind into the Indian grid requires domestic infrastructure deployment on a scale we haven't seen before.
But the international wins within that order book are what truly validate their global competitiveness. For instance, they recently secured a 34.75 crore order in Abu Dhabi.
Proving their ability to win high-spec tenders in the capital-rich Middle Eastern market.
Exactly. But there is another specific contract that reveals an entirely new, massive growth frontier. They secured a 48.3 crore reactor order specifically for a U.S. data center, which must be executed within 12 months.
Let's pause and dissect that U.S. data center contract, because this completely reframes the narrative. They aren't just a traditional grid modernization play. They have engineered a direct backdoor into the artificial intelligence boom.
It is a phenomenal strategic pivot. The global build-out of hyperscale AI data centers is constrained by one fundamental limitation: pristine power availability.
AI server racks, heavily populated with thousands of massive, power-hungry GPUs training large language models, require an ungodly amount of continuous, flawless power. If a traditional cloud-storage server experiences a tiny millisecond voltage sag, the system might pause, but it recovers.
But if an AI training cluster running a multi-billion parameter model experiences that same microscopic voltage sag, the highly sensitive tensor cores can physically fault.
Oh, wow.
The entire training run can crash, costing millions of dollars in lost computational time. AI data centers cannot tolerate the standard volatility of a local grid. They require absolute flawless power quality.
And Q-Power is manufacturing the massive reactors and harmonic filters required to insulate those U.S. data centers from the erratic grid, ensuring that pristine waveform.
It's fascinating. You don't have to pick which Silicon Valley tech giant is going to win the AI arms race.
No, you don't.
You just have to look at the heavy machinery supplier providing the physical hardware required to keep all of their server farms from shutting down.
It is the ultimate picks and shovels play for the AI revolution. And to maintain their edge in providing this hyper-premium equipment, Q-Power is aggressively scaling its internal R&D. They are investing 25 crores to build a new global engineering center in Sangli. And crucially, they are backward integrating their supply chain. They established India's first HVDC CTC magnet wire facility.
That CTC facility is a perfect example of their premiumization strategy.
Remind me, what is CTC?
CTC stands for Continuously Transposed Conductor. In a massive 765 kV transformer, you have huge bundles of copper wire carrying immense currents. If you just use standard thick copper cables, the electromagnetic fields create massive eddy currents inside the copper itself.
Which generates heat.
Intense heat, and it destroys the efficiency of the transformer.
So you have to weave dozens of smaller, individually insulated copper strands together in a highly specific, continuously transposing pattern to cancel out those eddy currents.
Precisely. Manufacturing CTC magnet wire requires incredible precision. By bringing that capability in-house, Q-Power reduces their reliance on highly specialized external European or Japanese suppliers, compresses their lead times, and captures the margin on one of the most expensive subcomponents of their entire product line.
It is a beautiful operational loop. The narrative is almost intoxicating. We have a mid-cap manufacturer sitting at the intersection of grid modernization, the renewable transition, and the AI data center boom. They have an expanding moat, massive operating leverage driving 301 crores in net profit, and a 1,400 crore order book validating their hypergrowth. It sounds like an absolute juggernaut. Exactly. But in public markets, when a narrative is this flawless, the danger isn't necessarily the business model itself. It is the expectations built into the valuation. Let's look into the abyss. We need to dissect the structural risks and the terrifying reality of the valuation cliff.
The primary risk vector for Q-Power right now is their own success. The financial markets have clearly recognized the massive structural tailwinds and the company's brilliant positioning, and they have priced the stock accordingly. Q-Power is currently trading at a PE ratio of 103.6x and a price-to-book ratio exceeding 16x.
A multiple above 100x implies that the market is paying for years of continuous, uninterrupted hypergrowth up front. It means the stock is priced for absolute, flawless execution. There is zero margin of safety.
That is the valuation cliff. When expectations demand perfection, any slight operational friction triggers a violent repricing. If a major domestic tender is delayed by a quarter, or if a shipment of specialized steel is held up at a port, causing them to miss a revenue recognition window, the fundamental business might still be fine, but the valuation multiple will collapse.
The execution risk at these levels is immense.
Immense.
And there are massive external forces threatening that flawless execution. Despite their specialized moat, they are still competing in an arena dominated by global giants. Siemens, ABB, and GE Vernova are not ignorant of the margins available in the EHV StatCom market. If those multi-billion-dollar conglomerates decide to aggressively defend their market share or prioritize specialized power quality systems, they have the balance sheets to wage a brutal, multi-year war of attrition on pricing that Q-Power simply cannot match.
You also have immense regulatory fragility. Generating 75.77% of your revenue from international exports is a massive advantage until geopolitics shift.
Right.
Q-Power navigates over 100 different national trade frameworks. They rely on strict NABELE accreditations and localized utility approvals. If a major export market suddenly implements protectionist tariffs on heavy electrical equipment or arbitrarily tightens its testing standards to favor domestic manufacturers, a significant tranche of Q-Power's TAM could evaporate overnight.
But the risk that I find most structurally terrifying is the inherent contradiction in their business model. What I look at is the cyclicality paradox. We established earlier that the fundamental demand for grid modernization is a 50-year irreversible structural megatrend.
Yes, the physical decay of the grid guarantees the demand.
But the funding mechanism for that demand remains deeply cyclical. The entities actually writing the checks for these 50 core StatComs are national utilities, sovereign governments, and highly leveraged EPC contractors. Their ability to deploy capital is entirely tethered to macroeconomic cycles, interest rates, and government fiscal deficits.
It is a profound vulnerability. If the global economy enters a sustained recession, or if central banks keep interest rates prohibitively high, the cost of capital for a utility to finance a massive offshore wind integration project skyrockets.
So they pause the projects.
Exactly. The utility might look at a degrading 40-year-old transformer and decide, we know it needs replacing, but we can't afford the debt right now. We're going to push it to the absolute limit and squeeze another 3 years out of it.
The structural need hasn't vanished, but the procurement cycle is violently delayed. And for Q-Power, who is currently deploying massive capital to expand factories based on immediate demand projections, a sudden freeze in global infrastructure spending leaves them with stranded capacity, crushing their operating leverage in reverse. And that cyclical funding risk exacerbates a critical operational vulnerability within their supply chain. Earlier, we noted that Q-Power manages its working capital by utilizing a just-in-time custom inventory model.
I want to push back hard on that premise.
Go ahead.
A just-in-time supply chain makes perfect sense if you were assembling smartphones using standardized microchips flown in overnight. But Q-Power is building 100-ton industrial machines requiring massive bespoke orders of cold-rolled grain-oriented steel and specialized copper matrices.
Yeah, heavy metals.
In a global macro environment defined by volatile shipping lanes, geopolitical choke points, and wild swings in commodity prices, relying on hundreds of tons of raw materials to arrive just in time for heavy manufacturing seems incredibly fragile.
It is a massive operational contradiction, and it is the fulcrum of their margin risk. The supply chain for specialized heavy metals is inherently illiquid and prone to disruption. If global copper prices violently spike due to a mining strike in Chile, or if specialized insulation paper from Europe is delayed by weeks of port congestion, Q-Power's entire JIT manufacturing schedule fractures.
Which immediately triggers a cascade of failures. If the raw materials are delayed, the manufacturing timeline slips. If manufacturing slips, the delivery date to the utility is missed.
And reputation is everything in this industry.
Right. Not only does that damage their reputation for reliability, which is their core competitive advantage against the capacity-constrained giants, but it brutally pushes back their revenue recognition, exacerbating the exact working capital trap we discussed earlier.
But the more insidious threat from that supply chain volatility is margin compression. Q-Power attempts to insulate itself by negotiating raw material pricing in advance and embedding price variation clauses in its long-term utility contracts, allowing them to pass sudden commodity inflation onto the customer.
But there is an inevitable temporal lag in those mechanisms.
Exactly. If Q-Power wins a massive tender today to deliver a complex HVDC reactor in 18 months, and the global spot price of CRGO steel skyrockets in month 9, the contractual mechanism to pass those costs onto the utility might be capped or delayed.
So they eat the cost.
The inflation violently compresses Q-Power's gross margins before they have the legal or operational ability to adjust their pricing.
So they are effectively trapped between two immense forces. They are engineering the bespoke, heavy hardware required for a multi-decade structural energy transition. But their day-to-day profitability is dangerously exposed to the chaotic, highly cyclical realities of global commodity markets, shipping logistics, and sovereign infrastructure budgets.
It is a high-wire act. They have built an incredible machine, but the tolerances for error, both operationally and in terms of their market valuation, are practically zero.
Let's pull all of these threads together. We began by looking at a mid-cap manufacturer out of Sangli, India, and we uncovered a company that is quite literally forging the physical backbone of the next century.
Yeah, literally building it.
Q-Power sits at the exact intersection of three unstoppable forces: the massive global integration of volatile renewable energy, the explosive power-hungry expansion of hyperscale AI data centers, and the desperate, non-discretionary need to replace a physically exhausted 40-year-old grid.
They have carved out a highly defensible moat by hyper-focusing on extreme high-voltage engineering, navigating the grueling regulatory requirements of over 100 countries, and brilliantly timing their capacity expansion to exploit a global supercycle shortage.
And the financial engine is validating that strategy, generating hypergrowth and massive margin expansion through a deliberate shift toward bespoke power quality systems, all anchored by a massive 100 crore order book.
Yet they are balancing on a valuation cliff. The market is demanding absolute perfection from a business model that is fundamentally capital intensive, plagued by elongated cash conversion cycles, and highly vulnerable to the whims of global commodity pricing and macroeconomic infrastructure cycles.
It is a breathtaking industrial balancing act. And it leaves me with a final thought, something I want you to carry with you. The next time you open a news app and see a headline about a major industrialized nation committing to net zero by 2050, or you read about a Silicon Valley titan breaking ground on a massive new multi-billion-dollar AI data center, don't just picture the sleek solar panels gleaming in the sun or the pristine tensor cores processing data.
Look deeper.
Think about the sheer, unsexy, heavy physical reality required to make that software-driven future possible. Think about the massive, highly specialized 765 kV transformers, the multi-ton STATCOMs, and the giant steel reactors submerged in oil that had to be meticulously engineered, tested, and shipped across oceans just to act as the shock absorbers for our fragile electrical grid.
The hardware that makes it all work.
Think about the fact that without this colossal hardware, that beautiful green AI-powered future instantly causes our entire electrical infrastructure to violently collapse. And then wonder, is there enough heavy manufacturing capacity left on this planet, enough raw copper and steel in the ground to actually forge this future into reality?